molar mass, think about what you had, what you just calculated, and then move on to how to get molar mass. So let's walk through number 10 very quickly. This right here was more to help you research some stuff we talked about yesterday and to get you some examples in your foldable. So if you didn't finish that, you can do that on your own. Number 10, here we go. Not number 10, what number is this? 19. 19. Question, make sure you write this down if you don't have it or if you had some mistakes or some confusions. 100 milliliters of the gas is collected in very large test tubes. So if you're given 100.0 milliliters, in the end, we might have to convert that to an appropriate unit. Just a second. The weight of the gas in the test tube is 2.62 grams. The gas was collected at 697.68 millimeters of mercury at 10 degrees C. What is the molar mass of the gas? Okay, so it's asking for molar mass. What units does molar mass have to be reported in? Grams per mole. Grams per mole. So from this information, what do we already have that's appropriate for molar mass? We already have the grams, and we know that grams is not going to go in the ideal gas law because there is no gram to go into the ideal gas law. And you know you can't convert this to moles because what do you not know? What do you not know? You don't even know the molar mass, so you can't use that to get to moles. So in the end, we actually do have grams. It's right here. We're going to use this at the very, very, very end of the problem. So really, what's the true question here? What are we looking for first? Moles, because it's mole that we still don't know, because these two things have to be used to get to molar mass. So our first question is, what is N? I did see a lot of people set that up correctly. So the real question is, what is N? So using this information, and I saw a lot of no units, nor did you rearrange your formula? Because what some of you guys are doing, you're putting your information in PV blank RT here, and then you're dividing the wrong way because you didn't rearrange your formula first. So I'm trying to protect you from mistakes. That's the only reason I'm kind of mandating this here. So I need to solve for N. So I'm going to divide by RT, and those cancel on this side. So what you would have rearranged to is N is equal to all this junk over here, PV over RT. Well, what unit does P have to be in since we're using this R constant? Atmospheres, right? So I did not give you atmospheres, I gave you millimeters of mercury. Who converted atmospheres? Thank you. Those of you who got 3 moles, you didn't convert to atmospheres. Okay? So can you guys tell me what that is converted to atmospheres? 0.918? Okay. 0.918 atmospheres. And I would show my work for that. Right now I'm just trying to expedite this. So that's times by 1 atmosphere over 760 millimeters of mercury, and that's how you convert from millimeters of mercury to atmospheres. And then what's the V have to be recorded in terms of its units? Liters. Do not multiply by 1,000, divide by 1,000, right? So move sweep the decimal back 3 spaces. That's how many liters? 0.1. Yeah, 0.1 liters. 0.1000 liters, really, but I'm going to write it like that for now. What is the R constant as a whole? 0.0821 atmospheres times liters over moles times K. So if you write this down, guys, I promise it'll trigger your brain to go, oh, I need to get to atmospheres if you accidentally put the wrong unit in there. So write that out so it triggers the brain to make sure every unit will cancel. And then the temperature is 10 degrees Celsius. What does that need to be converted to? 283 Kelvin. Good. So you're just adding the 273. So that's 283 Kelvin. There we go. All right. And then what units cancel? Kelvin here and here. Atmospheres and liters. Okay, so the only unit left is that mole again. So if you guys can do that, retry it, whatever you need to do. What's your mole? 0.0 what? 0395. 00395. 0.00395 moles. Okay, so that's our moles. And then I did see a lot of us got, not a lot, a couple of us did get that far. And then our grams that we had initially and our moles we just calculated. Remember, the units for molar mass are grams per mole. We're literally just going to divide. Some of you guys were kind of like multiply by the molar mass and have an X there to serve as its molar mass. You can just divide and it will give you the correct molar mass because the units are what they are. 2.62 grams divided by the moles we just got. So 0.00395 moles. Because what we're saying here is that grams that are here are equivalent to that many moles. The units come out to be grams per mole, and that's what molar mass is. So, Paige, can you do that for me too much? I think this is easier. 663 or 633? 663. grams per mole. Okay, so at the very end, when it's asking for molar mass, just take your grams, take your moles, and divide, and you're done. Okay, so we're going to have another problem like this today, but a little bit more complex. All right, so I'm going to give you guys 25 minutes right now to work through a simulation. If you can please go to my website and go to Unit 5, you're going to see a PhET simulation. PhET, P-H-E-T. That's not it. And there's a document under Unit Documents for Unit 5 that gives you a guide on how to get started. My computer's moving real slow. If you guys can pull it up, and then if you need a partner, you can partner up, because I know some people's stuff's not pulling up. So simulation is this link here. The activity is here. It requires you to draw a couple things and then make some manipulations to pressure, volume, temperature, and then go on and answer the questions there. So this is something you can just write on paper. And when I say work with somebody, I mean like sit there, talk. So everybody's writing down their own stuff. Okay? I'm going to try to keep it about 25 minutes because I need a little time at the end to go through gas stoichiometry. So when you click the link, or when you open the document, you'll see little boxes, and you're going to be drawing them. This is something you do before the simulation, really, because you don't need the simulation necessarily for that. But then it tells you where to go, and then move on from there. These can be short, quick answers. So the simulation kind of looks like this. You do have to like download it and open it back up. So, yeah, you need to use a desktop or a desktop open. You might need to, well, I think it's I'm logged in, but you should do verification. So it might be nice to have a simulation pulled up on one person's computer and then the document pulled up on somebody else's, unless you want to work by yourself.
Like try to open it, download it. Yeah. So then you should go to the top where I think where you're on. Then click on the open.
Yeah, I clicked on those.
Probably not.
All right, so on the simulation, I think most of us did get to part 2. This is the equation I want you to write down someplace near part 2. KE, kinetic energy, is equivalent to 1/2 mv squared, where m is mass. That's like your heavy and light species that it was referencing. And then v is velocity. And that's more like speed that you were noticing. Some of them were moving faster. So those particles that were in the container, were they all the same temperature or were they at different temperatures? So all the same temperature. And this is going back to the kinetic molecular theory where we were like, temperature is directly related to kinetic energy. So there has to be an equivalency, especially if we're talking about how temperature speeds up particles. Well, they have more energy, that's why they're speeding up. So there's this inherent relationship between temperature and kinetic energy. Well, if they're all the same kinetic energy, there has to be a relationship with its mass and its velocity, because you guys saw the heavy species. How do they travel? Slow, right? So are you telling me that's a direct or indirect relationship? Heavy species, so a high mass, traveled low speed. So direct or indirect? Indirect. Okay, so this, whenever anything's multiplied by each other and they're equal to a constant, and this is constant because we're at a constant temperature, of course, they have to be inversely related, because as one goes up, the other must go down, like here, for that kinetic energy to stay the same. So I want you to know that the heavier ones traveled slower. So that meant the light ones traveled faster. And you know that. That's how everything works. If I were on a cross-country team or, pass baton, I would be the slow one, okay? I would be the slow one, okay? So I would also be that we have in AP chemistry, we go over rates and rate determining steps. The rate determining step is the slowest step in a reaction. I would be the rate determining step, okay? So that's our relationship. I just want you to make that under part 2, because that's what you guys are experimenting with. We'll finish that on Monday, most likely. Okay, so this, I'm going to skip through the stuff we went through yesterday. We are now going to talk about gas stoichiometry. Now, I don't really want to write all this down. I want to talk to you first. Do you remember this. Do you remember that is a conversion? That's an allowed conversion at STP. Now we're using STP out the wazoo, right? Well, sometimes, oh, remind me, what is STP? I know it's standard temperature and pressure. What are the conditions? 0 degrees Celsius, which is 273 Kelvin, and 1 atmosphere is our pressure. So when you're given these conditions, and I asked for you to convert from moles of a gas, maybe you got, well, where would you calculate moles at? Using the what law? Which is one of the only laws with the moles. Ideal gas law that we went over yesterday. PV equals nRT. So maybe you ask a question. It's like, okay, get to moles. You got to moles. What if I said convert to liters of that gas? Well, if I ever want you to convert at STP, I'll tell you it's at STP. You can utilize 22.4 liters per mole, again, like we did in our last unit. Well, sometimes things are not going to be at STP. So how would you indicate the moles, or how would you convert to from moles to liters or something like that? You would not be able to use that constant. So you have to utilize PV equals nRT. Because a lot of times you'll be asked to solve for moles using PV equals nRT, and then later on you're going to have to get to grams. Well, that's pretty easy. We did that today. This was kind of using molar mass. And sometimes you'll have to go from grams to moles back to liters, and that's going to be using the PV equals nRT. Now, this is all in relation to a bigger reaction. Not just like, oh, I got nitrogen, let's calculate moles of nitrogen, and then volume. It's not going to be one species. It's going to be a reaction. So I'm going to backtrack from here. This is, I just want to make sure, STP, we use 22.4. Non-STP, we're probably going to have to use ideal gas law. So, if you have a reaction like this, let's just write down the VCE first. We remember we can like utilize mole ratios. Oh, dang it, I already have it right there. Never mind. Here's your VCE. Hydrogen gas, diatomic. Oxygen gas, diatomic, yields water vapor. If all of these are, I think they'll be blue behind. If all of these are gases and they're all at the same temperature and they're all at the same pressure, we actually can use something called, if we're going from volume to volume, let's say, right, we have 5 liters of this hydrogen gas and 4 liters of this oxygen gas. We can actually go with something to call a mole ratio, a liter to liter ratio. And it's only because gases allow us to do that when they're at constant temperature and pressure. Because those conditions, those temperature and pressure conditions, are the only thing that will ever change volume, really. So if we keep it constant, we're allowed to use a volume to volume ratio, which we call a liter ratio. And that's a trick that most people wouldn't know, but I'm trying to tell you that up front so that you don't waste your time going to convert to liters to moles, and then moles to moles, and moles to liters, if you can just go straight from liter to liter. So I'm going to kind of show you that here. Indicating the 5 liters here under hydrogen and the 4 liters under oxygen, I'm telling you there are 2 reactants, and I'm telling you there are 2 quantities. Do I tell you who the limiting one is? In this question right here. Do I tell you who the limiting one is? No. Do you remember how to figure out the limiting reagent? You're like, no. Okay, some of us. Well, you tell me. If I have 5 liters of hydrogen gas, or I'll go with the easier one. Let's go with 4. If I have 4 liters of oxygen gas, how much hydrogen gas do I need to fully react with all of the oxygen gas? Does anybody have an answer? I have 4 liters of this, right? Yeah. How did you get that? Okay, so in layman's terms, he says, if I have 1 mole of oxygen gas, I need twice as much hydrogen. So if I have 4 liters of oxygen gas, I need double hydrogen. Well, that means I need 8. So what's going to happen to the hydrogen if I only have 5? Is that one going to run out, or is that one going to be in excess? It's going to run out. Okay, so that's going to be our limiting reagent. I'll work with you on that more. So, but logically, I think you can make sense that you need double the hydrogen, so that's going to run out because you need 8 to react with all of that. So this one's going to be our excess one, and this one's going to be our LR. And the only reason we ever are concerned with finding the LR is because the LR controls the product. It controls how much is made. So this 5 liters is going to be my starting point to figure out how much is made of my water. That's our product. This is of hydrogen gas. So back in the day, when we didn't know about this liter to liter ratio, what would you do with this liter? What would you convert it to? Moles. How? 22.4, and that's assuming STP It does not say STP up here, but we would maybe assume right now because we don't know any better. So that would be 22.4 liters to 1 mole. And then we take our 1 mole of hydrogen gas to what? Who are we looking for? What are we looking for? What's the question? Liters of water vapor, okay? So we go from liters to using 22.4 to moles, and now we get us to moles of hydrogen gas, and then we go to moles of water using what? Remember mole ratio, 2 to 2? Let me show you. Let me write this down. I'm just getting a lot of blank stares, so let's make sure. So back when we had to convert to moles of hydrogen gas, liters of hydrogen gas like this is what you're comfortable with using 22.4. Then we would have had to go to water vapor from hydrogen gas. Well, that's a 2 to 2 ratio. And so here you would have written 2 moles of hydrogen gas to 2 moles of water vapor. Is this coming back to you a little bit? Okay, so then we're in water vapor, and the question is to liters of water vapor, so what would you do next? Okay. What would you do next if you had to do liters of water vapor? Say again, 22.4, right? Because this is the same thing, it's the same conversion, it's just on top this time. Liters per 1 mole. And that's a water vapor. So that whole process is hunky-dory, it's fine, we can totally do that. But I want you to notice that you're using 22.4 liters twice, here and here. And so instead of us always going to that, we actually can instead, you can see we're dividing by 22.4, multiplying, and then the ratio is a 2 to 2 ratio. We can use this 2 to 2 ratio. Instead of saying moles here, we could say liters here, and we can get the same answer. So this is what I'm saying is a trick. Whenever something is it's a gas and it's at a constant temperature and pressure, instead of going to liters, from liters to moles to liters, you can go straight from liters to liters. And I would put here 2 liters, right, of of water to every 2 liters of hydrogen, and that would give me 5 liters again. And that would be of water this time, not hydrogen gas. Because this right here, 22 cancels, and then 2 over 2 is 1 over 1. So you can see nothing really changes, it's just 5 liters again. And that's just because of the ratio. But this is a much shorter process, and you can use this as a trick if it's at constant temperature and pressure. Cool. Liter to liter ratio is just a different way of saying mole to mole ratio. So really, I want you to remember there are such things as mole ratios. So let's kind of work through a problem. I want to show you the big idea, the big picture here. Okay, this one is this on your sheet? Is this number 20? Oh no, this is not drawing. We'll do this one first. Number 20 is next. Number 20 is next. So I want you to work through this one with me. I want you to write down the givens with me, reactions, the whole shebang, okay? So first of all, potassium chlorate decomposes. So bring back your decomposition reactions in your head. What does the chlorate always make? What gas? O2 gas. Okay, remember, oxygen gas is made from chlorates. So potassium chlorate decomposes to make oxygen gas and what else? Which metal chloride? Potassium chloride. Okay, so then we need to balance it. What do I need? A 2 in front of here, and a 3 here. Okay, we've literally read the first like four words. When potassium chloride decomposes, we usually will need a reaction at 755 millimeters of mercury. What is that for us? Pressure. Someone's going to go ahead and label that pressure. 755 millimeters of mercury. And 23 degrees Celsius. So that's our temperature. 23 degrees Celsius. I already know I got to do what? So what's that in Kelvin? 296 Kelvin. Okay. 42.6 milliliters of the gas is collected. Well, what gas is that? Oxygen gas. So when it says the gas, it's talking about oxygen gas. So I'm going to label that when I write it down over here as well. 42.6 milliliters of oxygen gas is made, and that's our volume of oxygen gas. Okay, how much potassium chlorate must have decomposed if none of the gas was lost? So what's our question? What's the unit it's looking for? Grams of what? All right, so the question is grams of KClO3. Okay, so there's a big point to be we made here. All of this information, pressure, temperature, volume, who is it talking about? What identity? What compound? Oxygen, see? We even wrote it there, just to remind ourselves. This is all about oxygen. Everything here is about the gas. Okay, and considering we're in the gas unit, we're talking gas laws. All of our laws are regarding gases. So at the end, my question's about potassium chlorate. So it's not really asking about potassium chlorate up front. It's asking more about the gas up front. So what we need to do is focus on the gas. What do we not know about the gas from our variables here? The amount of moles of gas. So the first question is not grams of potassium chlorate. The first question is moles of oxygen gas. So if we can figure out how many moles of oxygen gas are made in this reaction, can I get back from here to here? Yes, I can. Once I get moles of oxygen gas, how do I get back to here? Moles, so this is, since I'm in moles, I'm actually going to use my mole ratio back that we're really comfortable with. 3 moles of oxygen gas is equal or equivalent to 2 moles of potassium chlorate. So then once you're in potassium chlorate, can you get back to grams of potassium chlorate? Shake your heads, people, yes or no? Molar mass, right? Okay, so let's walk through this together. This right here is not, you don't have 2 pressures, you don't have 2 temperatures, you don't have 2 volumes. So what gas law is this one? Say it again. Ideal. This is the ideal because it's not, since you don't have 2 pressures, 2 temperatures, and 2 volumes, it can't be any of those Boyles, Charleses combined, Gay-Lussac's. It can't be any of those because you don't have 2 pressures and such. So this has to be related to the ideal gas law, which is PV equals nRT, because this is all the information you have that I can plug in, and this is the only one that will work. So what am I solving for here? N. So I'm dividing by RT on both sides. So this N that I'm referencing is moles of oxygen. I like to label it just to make sure that no one forgets this is about oxygen right now, because we're talking about the gas. Now, my pressure here is in 755 mercury. Can somebody get that in atmospheres for me? Calculate. So in your calculator, you're putting 755 millimeters of mercury times 1 atmosphere over 760. So in your calculator, just dividing by 760, and what do you get? 0.9. I'm just going to go out a couple more, okay? 9934 atmospheres. Great. And then what else? What's going on top? Okay, so the RT over here canceled, sorry. N is equal to PV over RT. Volume in this case is, it has to be in liters, so we have to convert this to liters. So how do I do that? 1, 2, 3 back, so that's 0.426 liters of oxygen gas. We're still talking about the gas, because in a gas law, you cannot plug solids in, you only can plug gases in. R, yeah, sorry, I didn't transfer that all the way. There you go. Thank you. 0.0426. R constant, 0.0821 atmosphere liters per mole K. Who's accidentally already memorized that? All right, cool. You guys work out more problems. You can accidentally memorize it. You'll be writing that down quite a bit, units and all. Temperature, I've already luckily converted to Kelvin, so 296 Kelvin goes on bottom. And you guys calculate moles for me. Calculate. It's good to practice this so you make sure you put your numerator in correctly and your denominator in correctly. Anybody? 0.00174. I'm just going to expand 1 mole, okay? Because this isn't my final answer yet. This is just my stopping point because I'm now to oxygen gas. Now, this being moles, right? You're like, I'm done. Well, the question's not about moles of oxygen gas. It's about grams of potassium chlorate. So once we get down to our moles of oxygen gas, you guys, again, tell me, how do I get from gas of oxygen to this over here? All right, mole ratio. So I'm going to write that down here now. So 0.00174 moles of oxygen gas. I'm running out of space. Of oxygen gas needs to be converted to moles of potassium chlorate. And this is using our 2-to-3 ratio. So 2 moles of KClO3. This is old stuff, right? You remember that we did in fact learn this. Yeah, it's been a couple of days, but you got this. And that 3 goes on bottom, 3 moles of oxygen gas. So we've used our BCE, we're done. You guys have your BCE in your paper so you can see it. I just need to scroll down some more. So that gets us to moles of potassium chlorate. What's our last step? Right, and what's you guys calculate the molar mass of potassium chlorate? 122.55. Okay. 1 mole of potassium chlorate goes on bottom. 122.55 grams of potassium chlorate goes on top. And that's going to be our end unit, and that's what was asked for. So moles of oxygen cancel. Moles of KClO cancel. Grams of KClO was what we get. And you guys tell me what you get there. Point 142. Stopping at 3 sig figs because of this pressure and the temperature, and a lot of these things have 3 sig figs. So, and that's grams of KClO3. So we only need just a pinch of KClO3 to make 42 milliliters of oxygen gas. That's what that means. We only need that much KClO3 to decompose, which is just very little, in this reaction to make 42 milliliters of oxygen gas at this temperature and pressure. Okay, so I mean, you should pat yourself on the back. You did reactions, gas laws, and stoichiometry on one big problem. That's success right there, right? That was success. Okay, let's try it again. We have about 16 minutes. This one is the first of your 5. Look on the bottom of your paper. It says ideal gas law stoichiometry lecture problems. I'm going to try to help you set up at least reactions on some of these. I want to get through maybe 2 more, okay? So number 1, magnesium chlorate. Write it down. Let's do the BCEs at least. Because if you can't get the BCE, it's really hard to get started on the problem, and I don't want that to hold you up, okay? Ready when you are. What's magnesium chlorate? Mg. Cl. O. It's still chlorate, people. We just did a chlorate example. 3, and there's a 2 on the outside because of magnesium's charge. All right, chlorates, again, decompose to what? And here in magnesium chlorate, can you spell it for me? MgCl2, because you're still crisscrossing your charges. And oxygen gas, and then balance. 3 in front of the oxygen, we're good. Okay, I'm going to talk to you here before we move on to the next BC. Okay, so we got 45 grams of magnesium chlorate. Okay, that's about magnesium chlorate. That's not about the gas. It decomposes at that temperature. That much gas is collected. So now we're given 2 pieces of information. This is about the solid. 5.94 liters is about the gas at that pressure. What is the percent yield for the reaction? What is percent yield again? Okay, I'm here in actual over theoretical times 100. We have some of this already in the problem up here. What do we have? Actual yield, and what's that number? Okay, remember yield, guys, is always talking about reactants or products. Which one? Yield is products. You're yielding, you're forcing, you're making products. So when it's talking about this, it's actually talking about which product? The gas. Well, what's the gas? Oxygen gas. All this over here is going to be regarding oxygen gas. So actual yield is going to be what we actually collected. It's saying this person collected that much gas in the lab. So that 5.94 liters is the actual yield. Okay, so we know that much. What do we need to calculate? So the theoretical yield of oxygen, right? So they've done it in liters. So what is the theoretical yield going to be in? Liters. So that's a question, liters of oxygen gas. That's what I'm trying to help you see the future before you start calculating. So the question is liters of oxygen gas. Okay, if the question is D, and we have TP, so, and this right here, why is this going to be useful to us? Get that to moles of magnesium chlorate and mole ratio to moles of oxygen gas. So that will be our N of oxygen gas. So we'll have N for oxygen gas. We'll have P for oxygen gas. We'll have T for oxygen gas. We'll be looking for that last V, that liters of oxygen gas from PV equals nRT. And that will be how we'll solve for V. Okay, so we'll have pressure, which we have, temperature, which we have. N of oxygen gas will come from converting 4.50 grams of that magnesium chlorate up here. And your R constant's always there. So your V is your question. So I'm going to leave that for you. And I wanted to talk to you on how to get started there. Next one. Okay, I'm giving you a start on all of them. As many as I can. Oh, that's that one. Okay, reaction. Read it. This is on your sheet, yep. This is number 2 on your sheet on the very bottom. Ready when you are. All right, guys, what are the 2 reactants? Magnesium and what's that formula? H, yep, HCl, because it's H with a 1 plus, C with a 1 minus, crisscross, 1 and 1. Okay, what does that make, knowing it has to make a gas? Okay, because with us we're talking about gases. It has to make hydrogen gas, because hydrogen gets displaced, single replacement, right, by magnesium. So magnesium gets the chlorine, so magnesium chloride, right, Cl2, Cl2, and hydrogen gas, which is written H2. And then what do I need? A 2 here. Good. Okay, so we've got our reaction balance. Gas, right? This is who we're really focusing on towards for the PVs and RT part of things. Okay, so 1.5 grams of magnesium is placed with 150 milliliters of HCl, or 0.1 molar. Ooh, I see volume and molarity. Those do not pertain to the gas. What do I need to do with this? Get to moles. So these 2 things here, that's our M, big M times V again, to get to moles. Do you remember that? Barely, I know, but it's there. This is in grams. Uh-oh, I've got 2 reactants again. 2 reactants with 2 quantities. I don't know who the LR is. So I'm going to have to figure out for my reaction, once I take this to what? Moles, right? I need to figure out who my LR is. So question 1 is, who is LR? We'll get there, okay? So that's what the first sentence is telling us. Question, what volume of gas? So what's my question? V, right, volume of hydrogen gas. That's my question. Could be collected if, or at that temperature, that pressure. That's our T and P. If a student captures that much gas, what is the percent yield? So this is a loaded question. So at the very end, when I ask for percent yield, I want you to tell me what we do know. What do we know? Which one do we know? Because it says the student actually captures 149 milliliters. So this right here is 149 milliliters of gas, of hydrogen gas. So do you see that our questions correspond? This theoretical yield was what this is asking about. Because it says what's the volume of gas formed. Theoretically, right, through the mathematics that we can calculate here, we're going to calculate theoretical yield when we calculate that hydrogen gas. So when we calculate, we can do calculation of percent yield at the very end. Now, LR part. This will give you a number of moles. This will give you a number of moles. Can you talk through with yourself? If I had 1 mole of magnesium, how much HCl would I need? 2, because it's a 1 to 2 ratio, right? So if you don't have double of hydrogen gas, or hydrogen chloric acid that you do of magnesium, if you don't have it, what's going to happen to HCl? It will make it. It will run out. You're going to have that be your LR. And then from there, if that's the case, I'm not sure, I have to look at my key. If that runs out, That's your LR, and that controls how much of this gas is made. In what ratio? A 1-to-2 ratio. That one I want you to try. If you like looking at all your big BDA charts, you can go back and look at your notes. Okay, let's set up number 4, because it's got this weird term, oxidation state, okay? Read it first for me. I'm glad you guys are jotting down some of your little notes, because it'll help. You'll get stuck, and you'll go back to your little notes and say, oh, we have to find this, we can find that. Okay, so unknown metal, what's its charge? 2+. It says oxidation state, that just means charge, okay? So that's our metal. I'm just going to put M2+. Okay, so that's our metal. It has a mass, okay, cool. It reacts with excess sulfuric acid. Is this a limiting reagent question, or do I already know who the LR is? I already know. Who is it? The metal, because it says I have excess sulfuric acid, so who cares? I don't need to really go through that BDA chart and LR. I know who the LR is, because it says it. So magnesium, or what is this, metal, reacts with sulfuric acid. Which sulfuric acid? Acids always start with H. Okay, so that's not hydrosulfuric acid, so it's got to be one of those ternary ones. What does sulfuric come from? Sulfate. What's sulfate? SO4 charge, 2 minus, because that 2 goes down there. Okay, so we have a metal, sulfuric acid. What gas is going to be made here? Oxygen. No, because what kind of reaction is this? What kind of reaction is this? Steam replacement, yet again, it's just a metal. And I'm going to erase the 2 charge for now, because we know that that oxidation state means 2 charge. This itself does not have the 2 charge just yet. It will over here. But I just wanted you to know that's going to be the one with the 2 charge. So metal and hydrogen switch places, steam replacement. So the metal gets with sulfate. Well, what does metal being a 2+ charge sulfate make? Criss-cross your charges, so the charges still exist there? No, because it's 2 and 2. So that's SO4. No 2's involved because they've already canceled each other out. And hydrogen gas, again, is made. So now that's our balanced chemical equation. So in this question, the mass of the original solid is given, the milliliters volume of gas is given, the temperature is given, the pressure is given. What is not given about the gas? The what? The moles of the gas, right. So you have volume, temperature, and pressure. Of course, all of these need to be converted to appropriate units. You're looking for moles of the hydrogen gas, okay? What is the molar mass of the metal? Okay, well, can you guys immediately find M of hydrogen gas? Do you have enough information to immediately find that? Tell me what you need. What formula is going to be used to find this? PV equals nRT, right? Do you have pressure? Do you have volume? Do you have R? Do you have T? Yes, you can immediately find that. Step 1, find N of hydrogen gas. Okay. The next question is, what's the molar mass of the metal? Well, what pieces do you need to find molar mass? We just did this for, like, homework. What pieces do you need? What units are molar mass? Grams per mole. Okay, so the question for molar mass is grams per mole. And this is for the metal, right? This is not for the gas. In this case, do you have grams for the metal? Look up here. Do you have grams for the metal? Yes, you do have this. Do you have moles for the metal? No. So you must find moles of metal after you find moles of the gas. How are you going to do that? How are you going to go from moles of gas to moles of metal? Mole ratio. Moles of gas to moles of metal. Right? So 1 to 1. So I think you can do this. You just need to do a little bit of math. Right, so I think I've set up 3 of them. I'd like for you to finish these. And I know you might have a little bit of hard time on some of them. I want you to finish 1 through 5 as best you can, so we can go over them Monday. And then we won't finish PS14. There's a couple things on there we're going to review Monday. Laws, Dalton's Law, and Graham's Law. But our test is supposed to be Wednesday next week, okay? So we're going to try to finish this up with our lab on Monday. Today, Tuesday. That's Monday. That's my goal. So lunch of the scientists, we go both teal, so you just go to one of them. So you can sign in at lunch of the scientists for teal. I have some B tickets. Yeah, I only have B tickets left. Okay, teal A seems like it's full. But there are like 16, 15 scientists coming. You guys can come, bring your lunch, chat with them, talk to them about their education, about what they do and their daily experiences. Talk to them about what they were thinking at your age, like how did they figure out what they wanted to do. Pick their brains about what they wish they could have done. Pick their brains about if they have, advice. So other than that, I'll be there.